Now I would like to introduce to you a very popular test device for pavements. The name of the device is the falling weight deflectometer, or FWD. And the device is shown here. It is this machine that is towed by a vehicle. And the idea is displayed in this video. So the device is pushed or pulled to a point of interest where a test is requested. And then the way it works is there's a circular plate that is lowered onto the pavement surface. And this plate is loaded by dropping weights on top of it. You can see this is the weight arrangement. It looks like those weights in a weight room, in a gym. And if we take a closer look at the device, this is what happens. So the plate shown here is loaded onto the pavement surface, and then the loads start being applied on the surface. And in this case, to change the load level, instead of adding weights or removing weights, the loads are just lifted up and dropped from a higher position. And that generates larger stresses or larger forces on the plate. If we look more closely, this device is equipped with a beam, and this beam has sensors that are coupled to the surface. And when the plate is loaded, these sensors are sensing the vertical displacements of the surface at different distances from the loaded area. Now the plate is made of metal, but it is coated below with rubber to ensure that the stress distribution is uniform as much as possible. And the sensor beam is measuring the displacement at different distances from the plate, but also there's a sensor that measures the displacement at the center of the plate. So overall, we have, from this device, we have the ability to apply a load on the surface over uniformly distributed over a circular area. We have the ability to measure the intensity of the force being applied, and then by dividing by the area of the plate, we can estimate the stress being applied, the stress intensity, and in addition, we have the ability to measure the vertical displacement of the pavement surface at different distances from the loaded region, including inside this plate there is a sensor to measure the displacement at the center. Okay, so how is the FWD so useful for pavement evaluation? So in many cases where we have an existing pavement, the properties of this pavement are unknown because of the time elapsed and the damage that it incurred. So if we assume that our pavement is a half space characterized by elastic modulus and a Poisson's ratio, so basically these are unknown and we are looking to find their values. The FWD helps in this respect because by bringing a load and applying it over a circular area, we are able to calculate or evaluate the elastic modulus and Poisson's ratio. What I'm drawing now is the deformation of the pavement due to the load itself. But now we have a measurement, let's call this D0, a measurement of the displacement, the surface displacement just below the load, and also we have some other measurements, let's call this D1, of the surface displacement at some radial distance from the loaded area. So just remind you, when we are dealing with a point force, the vertical displacement of the half space, this is at the surface, is given by the expression P, 1 minus Poisson's ratio squared, divided by pi E R. And for a circular load, this was a point force, this is circular load, the vertical displacement at Z equals 0, but also R equals 0, is 2 times 1 minus Poisson's ratio squared, QA divided by E. So with this FWD experiment, we have UZ measured. We have the measurement just below the center of the load. This was D0, and the measurement at some radial distance This is D1. So that means that we know these two values, we measure them. In addition, Q and A are known. This is the radius of the loaded plate, and this is the stress intensity. And if we are looking at T1, P is the overall load applied over the plate, so that's Q pi A squared, that is P. And so the radial distance at which D1 is evaluated is also known. So in effect, we have an unknown Poisson's ratio and Young's modulus. We have an unknown Young's modulus and Poisson's ratio, but this is the same half space. And we have two unknowns, but we also have two equations where everything else is known except E and nu. And that means that we are able to evaluate the elastic properties from solving these two equations. Now, of course, if we have more sensors and we are measuring the displacements in many more locations, we have an overdetermined system where we have more equations than unknowns, but then we can evaluate maybe more precisely E and nu in taking into account that the sensors that are measuring displacements are not perfect sensors. There's another reason why we like to measure at more points. I will explain that later, but for now, just think of this process as an inverse process, because previously we were given the Poisson's ratio and the Young's modulus and the load at the surface, and we are interested to evaluate the displacements. Now we are facing with an inverse problem where the displacements are known, the loads are known, but the material properties are unknown. So this process is called in pavement engineering inverse analysis, or another name for it is back calculation, where we are doing the reverse. Now, the procedure of measuring with an FWD that provides the deflections at the surface in the vertical direction, or another way to name this deflection shape is deflection basin, is actually to calculate the material properties of an existing pavement. Now, we use the half space approximation, which is really a crude first order approximation. In reality, and this is what is done routinely in design offices, is to consider the pavement as a layered system, where each layer is elastic and governed by two elastic parameters, Poisson's ratio and elastic modulus, that these parameters are different from layer to layer. And that is why we like to have the deflection basin measured at many points, because then we can make more equations and we can try to back calculate or perform inverse analysis of the different properties of the different layers. Usually in this calculation procedure, we assume that the layer thicknesses are known, so we do not have to estimate them from the back calculation procedure. The assumption of the materials being elastic is very common, usually linear elastic. And of course, the surface load is the FWD load, so it is fully known and measurable. There's another assumption that is made, and that is regarding the interface conditions between layers. It is usually assumed that they are fully bonded in the case of asphalt layers, in the case of asphalt pavements, and in the case of concrete pavements, the interfaces are assumed to be slippery. So with these assumptions and a known load and a deflection basin at the surface, it's a routine engineering task to perform back calculation and estimate the different moduli of the different layers. And usually what we like to do is to assume the Poisson's ratio values a priori based on the material type. The value of the Poisson's ratio it can theoretically vary between 0 and 0.5. And usually it is around 0.2, 0.3, 0.4, and the actual value does not make much difference or is not influencing much the results. So it is common to simply estimate or to simply assume a priori the value of the Poisson's ratio. Now, I was teaching you how to calculate deflections in a half space, and there is a technique to estimate the deflections in a layered space using half space solutions. And the idea started with Palmer and Barber in 1941, and then Odemark from Sweden improved the technique in 1949, and then Per Ulitz did his PhD here in DTU and developed it further. The method is called method of equivalent thickness, and the idea is to be able to solve a layered half space using half space solutions. And that is explained next.